Most people picture a lump of coal squeezed into a gem until it sparkles. That image is wrong twice over. Coal is a crustal rock that never visits the depths where diamonds form, and natural diamonds grow from carbon-bearing fluids in the mantle rather than by crushing graphite in one heroic squeeze. Hollywood loves the coal myth because it is simple and visual, but geology replaces that story with something stranger. Carbon that waits billions of years for a narrow window of pressure and heat. When either temperature or pressure slips out of that window, the same element becomes graphite instead, which is why pencil lead and gemstones are chemically identical yet physically worlds apart. Educators still fight the Superman image in classrooms because sticky myths travel faster than phase diagrams. A useful thought experiment is to ask where coal actually forms, near the surface, in sediment, and then compare that depth scale with the hundreds of kilometers required for diamond. Graphite in pencil lead and diamond in an engagement ring share one element but divergent bond geometries, which is why the myth collapses the moment you look at a phase diagram. Popular culture keeps reviving the coal story because it offers a tidy before and after, yet mantle metasomatism has nothing to do with swamp carbon compressed in the crust. Science museums still display rough crystals beside graphite blocks so visitors can feel the density difference that pressure creates over geologic time. Once you separate the element from the myth, the real story becomes stranger. Carbon waiting in the deep earth for a window that almost never opens. Natural diamonds crystallize in the upper mantle, typically between 150 and 200 kilometers down, where temperatures run from about 900 to 1300 degrees Celsius and pressures exceed 50,000 atmospheres. They do not form by directly compressing graphite. They grow metasomatically as carbon-bearing fluids migrate through host rocks and precipitate when conditions cross into the diamond stability field. Many gem diamonds are astonishingly old, on the order of 1 to 3 billion years, making them time capsules of deep earth chemistry long before dinosaurs walked the surface. A separate class called super deep diamonds can originate still deeper, in the mantle transition zone, carrying mineral inclusions that tell geologists about regions no drill has ever reached. Those stones rewrite exploration models because they prove that diamond formation is not confined to a single shallow story. The Hope and Cullinan diamonds belong to that deeper family, which means some of the world's most famous gems record physics from hundreds of kilometers down. Geochemists pair inclusion ages with isotope signatures to reconstruct the fluid histories trapped inside individual crystals. Craton roots provide the thick, cold lithosphere that keeps mantle fluids in the diamond stability field long enough for crystals to grow. Without that geologic refrigerator, the same carbon chemistry would route toward graphite instead of gem rough. Mantle fluids can carry carbon dioxide, methane, and water in mixtures that shift with temperature and oxidation state, deciding whether graphite or diamond wins. Peridotite and eclogite host rocks tell different inclusion stories, linking some stones to ancient craton roots and others to recycled ocean crust dragged deep by subduction. Oldest dated gems from Canadian mines push past 3 billion years, nearly 3/4 of Earth's age, which is a humbling scale for any narrator describing gem rarity. Diamond growth can continue across multiple geologic eras before a kimberlite finally offers an exit route upward. Transition zone inclusions, such as ringwoodite, hint at water stored deeper than most planetary models once assumed, tying gem stories to global geochemical cycles. Exploration geologists now map craton thickness with seismic tomography before anyone commits to a billion-dollar mine. For a diamond to reach your hand, something violent has to happen fast. Kimberlite pipes are narrow volcanic channels, carrot-shaped routes that blast mantle material through thick continental crust in geologically rapid eruptions. Diamonds are metastable at the surface. Given time and energy, they would revert toward graphite, so the speed of ascent matters as much as the depth of formation. No human has ever watched a kimberlite eruption in real time, and what exactly triggers these events remains an active area of debate among geologists. Indicator minerals such as chromium-rich pyrope garnets help explorers find buried pipes long before anyone digs a mine. Major diamond fields cluster in Siberia, southern Africa, Botswana, Canada, and Australia, each tied to ancient cratons where thick lithosphere preserved the right chemistry. Lamproite offers a rarer alternative host rock, famously at Argyll in Australia, where pink diamonds made mining history. Xenocrysts in the magma are pre-existing diamonds picked up during the violent ride, not crystals grown from the kimberlite melt itself. Exploration teams combine magnetometry, gravity surveys, and indicator mineral chemistry to narrow where a buried pipe might justify the cost of a drill rig. Once a pipe is found, the scale of effort is staggering. Open pits can span a kilometer across and plunge hundreds of meters deep, while underground operations chase ore bodies still farther down. Processing requires multi-stage crushing calibrated so hard diamonds survive, even though toughness is not the same as scratch resistance. X-ray fluorescence sorting exploits the way diamond glows under X-rays, separating gem rough from industrial grade before cutting plans begin. Only a minority of mined material becomes jewelry. Most diamonds serve industry as abrasives, drill bits, and precision tools where extreme hardness pays rent. Cutting and polishing can take weeks because only diamond reliably abrades diamond, and a single misdirected blow can shatter a stone along cleavage planes. Certification labs then grade cut, color, clarity, and carat weight before a gem enters the market chain that connects mine to showroom. Sorting houses must separate industrial grit from gem rough, even when both look like dull pebbles to the untrained eye. Conflict diamond certification schemes changed how rough is tracked, even if gaps remain in artisanal supply chains. Laser pre-cutting plans, weak cleavage planes before bruting begins, protecting value locked in a rough crystal. Industrial buyers order micron-grade grit by the ton, while gem houses chase individual crystals measured in carats. Mine planners balance ore grade against energy cost, because moving kimberlite is as much an engineering problem as a geologic one. Laboratories now recreate Mantle physics on a compressed timetable measured in weeks instead of eons. HPHT synthesis places graphite under roughly 5 to 6 gigapascals and about 1500 degrees Celsius inside massive hydraulic presses, using metal catalysts to grow diamond on a seed over days. CVD synthesis, dominant for colorless gem production today, grows diamond layer by layer from a methane-hydrogen plasma at lower pressure, often across 6 weeks in reactor chambers like those documented in Surat's green labs. Chemically, lab-grown and natural diamonds are the same crystal. Distinction requires instrumentation, not naked-eye guesswork. Market share for lab stones has climbed sharply, with industry sources reporting roughly 20 to 25% of the overall diamond market by the mid-2020s, though exact figures remain contested. Memorial diamonds grown from cremated carbon illustrate how the same crystal physics can serve ritual as well as industry. Post-growth annealing can remove brown tints from CVD plates, another step viewers rarely see when they shop a display case. Colorless plates dominate gem CVD output because low nitrogen content reads as water-clear under grading lights. Fancy color HPHT stones still matter for yellow and blue niches where dopants are deliberately introduced. So what makes a diamond scientifically interesting beyond sparkle? Its tetrahedral lattice gives the highest scratch hardness known in nature, yet brittleness means impact can still fracture a gem. Thermal conductivity exceeds any other natural material, which is why industrial diamonds cool cutting edges, and why engineers experiment with diamond in electronics and quantum sensors. Optically, high refractive index creates fire, but cut geometry decides whether light returns to the eye or leaks away. Natural stones carry billions of years of mantle history in their inclusion suites. Lab stones carry identical chemistry without that geological passport. The trade-off is not fake versus real. It is ancient messenger versus modern replica, industrial tool versus romantic symbol, and the episode's job is to hold both truths without marketing hype. Viewers who remember only the sparkle miss the material science story that makes diamond indispensable outside jewelry cases. Jade proves the opposite lesson: toughness without extreme hardness, reminding us that Mohs scratch tests are not the whole material's story. Whether a stone formed in a craton root or a reactor chamber, the lattice constants are the same. The drama is in the history, not the chemistry. De Beers' marketing history shaped how Western audiences linked diamonds to romance, yet the material itself was industrial long before it was symbolic. Understanding both threads keeps the episode honest without surrendering wonder at deep time and extreme physics. Next time you see a tiny facet flash, remember you are looking at a courier from a part of the planet no human workshop can fully replicate, unless it is the kind that runs on plasma and patience.